This conference will now be recorded.
So we'll start with the scenario that I have one flip-flop, T flip-flop. D is the data and I have connected one clock here. And here after this, I will have various logical gates like AND or, and the signal will be going through like lot of combinational logics. It can be adder, subtractor, but not a sequential element in between this. And here I am passing that data to another flip-flop, and this is also connected to same clock. So in terms of the clocking signals, I'll have like 50% duty cycle clock. Just assume that at this rising edge, if I launch the data, that is like the data what is there here, it is launched at Q. Okay, so I mean at this rising edge, I'm capturing the data at this flip-flop. Okay, flip-flop. That data has to transfer from here to here, right, to the input of another flip-flop. You can say this is F2 and F1. Here we will have some delay. It's combinational delay, and I expect that this delay or whatever we have, by the time like somewhere in advance, somewhere here, because at this edge I'm capturing the data here at this flip-flop. So I assume that at this point, slightly before the rising edge of the data is ready, this guy is ready, the data is ready, so that ready and stable, so that I can capture that data here at this rising edge. So the margin required, the time before this next rising edge, where the data has to be ready, right? Time before the rising edge of the clock, where the data has to be ready, we call it as setup time. Setup time. After this rising edge also, so internally he has to stabilize that data, right? I mean, internal to that, like we will have a lot of transistor circuits, so that like I have to hold that data sometime, so that like I can capture that efficiently, correctly, right after this rising edge. The time which where I have to hold that data, so that like the data can be captured internally, we call it as hold time. So in layman term, so from the rising edge, just before the rising edge, where my data has to be ready, we call it as setup time. After that, where my data has to be stable after rising edge, how long it has to be stable so that I can capture data correctly, we call it as hold time. You can think in this way. So this is the point where train arrives, right? This is the point where train arrives, you assume. So you have to be at the platform slightly before, sometime before the train arrives, right? So that we call it the time with which, like, where you have to arrive to the railway station, so that you can capture the train. We call it as setup time. After that, we have to, actually the train has to stop for some time, or else what will happen? People has to get into that train, right? People has to get into that train. So the time which like the train, at least which it has to stop in the station, so that people can get into the train. We call it as hold time. That analogy you can use. Okay. So for resolving the setup time, we have two ways. Either, first way, either I can decrease the speed of clock, decrease speed of clock. So if I decrease the speed of clock at this rising edge, I will capture the data. Whenever I say I am decreasing the speed of clock, basically I am pushing this next rising edge somewhere far away, right? Somewhere far away. So the time of arrival basically is fixed. This logic is fixed, right? So this is like still I may be like receiving somewhere here. He will be ready. So one way is to decrease the speed of clock where I am pushing the next edge of clock farther away. Second way of solving the hold violation to reduce this delay. Reduce this delay. I can reduce this delay by using or changing the architecture of this combinational logic, or people what they do, they go for a method called pipelining where they split this combinational logic into small chunks and they will insert another flip-flop there. So now my setup and hold violation will be between these two flip-flops. So previously I had A and B where I was analyzing between these. Now I will split this logical gate into small chunks and I will introduce another flip-flop. So now my timing analysis will be A and C and B. So this mechanism we call it as pipeline. So these are the two common way how we solve the setup and hold violation.
Hello.
Setup violation, sorry, not hold violation.
Hello.
Yes, Swarna, you can go ahead.
So, when we say we'll decrease the speed of the clock
Hmm.
for the setup violation, then we cannot choose any random clock value, right? Like
Yes.
we need to have some
So,
calculation
right,
based on that we'll use.
right. Yes, you are right. So I missed that point actually. So here I said first way is like decreasing the speed of clock. This is not an efficient way of using, because uh, whenever I say I am designing something, I cannot keep decreasing the clock because there will be some system requirements, right? So for instance, you are designing some communication system where it requires some 128 mega, that is like standard defined clock, where uh, at that speed you have to operate. So the first way is not a good way actually. I mean, you are reducing the performance of the entire design itself. So that is not recommended one. That is not recommended one. So second one usually we go with that.
So, is there any like calculation, any way if in case we need to decrease the clock, like we need to follow the first one? So, is there any specific way that we can choose the clock?
Yes, actually, if you see your after synthesis of your FPGA design, right, you will see F max of the design in the synthesis report. That is the maximum frequency with which you can operate. That is actually, see, like we have something called critical path, right? That is the longest combinational path what we have, and usually this timing violation, we see it in the longest combinational path, right? And based on that, the tool will derive the F max. So this timing violation will appear only whenever you are actually exceeding that F max. So you have to be like, you have to reduce the clock such a way that you are not exceeding the F max. So if you are not exceeding the F max, then definitely you will not be seeing any timing violation. So in the synthesis report, you can see that actually what is the F max is achieved in the design. Hope I'm clear.
Yes, sir. Yes.
Yeah. So how to resolve the hold violation? Hold violation, usually the amount of data which I hold, right? I mean, so after this, I have to hold for a longer time. I have to stretch the data pulse, right? I have to hold for longer time so that my hold violation will not be there. I mean, what happens? Usually if it is a synchronous, right? I mean, it is clocked, the data is clocked, then hold violation, it's like rare case where you see it in FPGA based designs, because FPGA is designed such a way that you will not get a hold violation. But in there will be some exceptions where you may see that, like due to logic what you design, you may see like whenever there is a CDC paths, in such scenarios you will see hold violation. Basically, you have to make sure that data width is sufficient enough so that you can capture properly at the receiving edge. Okay. So there will be some scenarios where uh, the data, right, like within the same domain also, what happens if you have two clock domain of same frequency, like slightly shifted. In these scenarios, what will happen? So if you are launching the data at these edges, so if you are capturing at these edges, so there will be like at this point, right? So the data will be like still taking some time to settle. Okay. So during when it is settling, if you try to capture this data, right? So you will here you will see like either high or either low, right? Neither high, neither low. It's like meta stability state, we say, in between states. So always, whenever you are dealing with like two such clock domain, it can be same frequency also. Many people think that like if both are same frequency, then we need not synchronize. It is not true. So even if it is same frequency and there is a phase difference, okay, there is a phase difference, then we have to go for something called double flop synchronizer. So whenever, like it can be like from external source also, you are receiving some data, what usually we do, we go for double flop synchronizer where two flip-flops are connected back to back. So this D, here one D, and this is Q, and this two flip-flops, the clock domain is C2, clock 2, which is capturing clock. Okay, so we'll have one launching clock, clock 1. So the data can be launched at clock 1, but at the receiving end. So here at the input, you may see this quasi state, right? So when you go through this double flop synchronizer, and again, like more the reliability you want, you can go with the more flip flops, okay? So that it will be stabilized, the data will be stabilized. And you can you often hear, so this is actually like whatever we were discussing, that is static timing analysis. We are not bothering about what functionality that circuitries are doing, right? So we are bothered about only timing aspects. So there is another analysis, we say that dynamic timing analysis, that is nothing but your simulations. So in the simulations, what you do, like the timing simulation when you run, so you will be validating the functionality, right? I mean, there you are not bothered about like whether setup time is met, hold time is met. So you are like bothered about whether my functionality, all the corner cases are working fine or not, right? That mechanism, we call it as dynamic timing analysis. You don't hear this term often, quite often, but uh, it is also actually like, I mean, because like that is like mostly what we do, like it's a simulation, right? So that is, we call it as dynamic timing analysis. But static timing analysis like slightly exceptional. So here we are not bothered about functionality. Here we bothered mostly on what is the delays, what are the delays. So we deal with delays. Okay. So another common question people will ask, what is CDC? In the timing, you might hear something called CDC, right? What do you mean by CDC?
Clock domain crossing.
Yes. What is the meaning of it? Why do we use that? Where do we use it?
If a right technique for synchronization or not applied, whether the
Pardon?
data loss, when the data loss will be happen.
Yeah. So actually, it is majorly deals with the frequency of the clock, right? So, uh, so like I have a two frequency datas. Okay, so one data which is operating at, like, let me give you an example. So I have one clock this way. This is of frequency 1. So if I have one data with this clock at this rising edge, if I want to pass 1 0, then it is like this, right? And you assume here one more data. I have another slower clock. Okay, so let me assume you have further clocks here also. I have another slower clock which is of frequency half of this. So this is frequency 1. This is frequency 2. I want to capture at frequency 2. What issue do you face here? This is data, okay? This is data. These are two clocks. What is the general issue you face here?
Data loss.
Which so actually at the capture end, which are the data? So here it is like it is 0, this is 1, 0, 0, 1, 0. This is the data what I am trying to transmit. So at the receiver end, what it is captured actually? At the receiver end, what we capture? So receiver
Value
clock
0
is this one, right? So we basically capture 0. This is lost actually completely. This we do not capture anything. So here we again capture 0. Here we do not capture. This 1 we can capture. I mean, even if I say I want to capture these two ones, out of that I will capture only one signal, right? One pulse. So this is, we call it as this is the common issue what we face in clock domain crossing. The reverse way also possible. I mean, see what happens. This is actually like I'm launching the data at faster clock and capturing at slower clock. So here in this scenario, what will happen is data loss. Data loss. So if I go for the reverse scenario, if I am launching it, sending the data at lower speed and capturing at higher speed, what will happen? What is the issue you will face?
Set of values, sir.
Pardon?
metastability.
Not metastability. What is going to happen is same data will be captured multiple times, right? If I, so here, if I send one pulse at this clock, for example, here to here, if I make it high and then low, if I send something like this, if I send something like this, so at this clock edge, what he will do? 1, 1, and 0. So instead of single 1, he is capturing twice, right? So multiple times it will be get captured. So for resolving this technique, for resolving this issue, we use some technique called data stretching and pulse detection. So in data stretching, what we do is, so at the lower frequency, so for example here, right, here, wherever there is ones, that one I will stretch for multiple clock cycles, multiple clock cycles. So this we call it as data stretching or pulse stretching, pulse stretching. For the reverse way, so if I have one big pulse which is coming at the lower frequency, then if I want to capture at higher frequency, wherever there is an edge at the receiver clock domain, I will do the edge detection and I will make a single pulse, and that single pulse I will detect. Okay, so this way we can pass the signaling. I mean, if it is a data, so usually, so this is actually for the signaling I am saying these two techniques. If it is data, then I may have to go for something called FIFO synchronization. FIFO synchronization. In FIFO synchronization, what we will be doing? we will take the asynchronous FIFO. We will write the data at write clock and get the data at read clock. So it can be asynchronous FIFO. This is the data transmissions, but if it is like signal transmission, we go with pulse detection or pulse stretching. Any questions? Any questions?
No,
No.
sir.
Oh. So another common question what people will ask in the interview is they will give you some circuitry with flip-flops and combinational logics, and they will ask you to find the delay, right? So find the timing paths and like what is the maximum frequency, all these things. So let's see some of the circuits. I have one buffer A, and this is 1 nanosecond, and I have a gate, logical gate, which has a delay of 9 nanosecond, and it is passed to 6 nanosecond. Okay, then we pass it through this will be output Y, and we will have another buffer where we will pass the clock. Okay, where we'll pass the clock, and this data will be going through flip flop, and we have another flip flop, and the clock through one buffer is here, it is connected here, and the data D and this Q output, right, we connect it here, and this also, this output and this output, we AND it, and this is passed through a flip flop, we'll just remove this, and same clock is driving this also, and here this output again it drives this AND gate, and also this output whatever this output is there, right? This output and this output, we pass it through one OR gate, and that OR gate is actually driving this. And this AND gate has 7 nanosecond delay, and this OR gate has 8 nanosecond delay, and this buffer has 2 nanosecond delay. So the flip-flop characteristics, T setup is 3 nanosecond, T hold is 4 nanosecond. Clock to data delay, from here to here delay, T clock to data, we have 5 nanosecond. These are the delays. So we have to analyze various paths here. Okay. So one is actually data to data paths. Okay. First we will see register to register path. Register to register path is nothing but flop to flop. Can you tell me which are the flop to flop paths? So from here, we have this, right? Flop to flop path. So here, this way, and this way, and this way. This is one path, right? And we have another path, this path, right? And this is also one flop to flop path, right? No, not that. Only two flop to flop paths are there. So what is the delay of this flop to flop path? First one, can you tell me what is the delay? Is it 7 nanosecond? Hello, am I audible?
Yes, sir.
What is the delay? So it is not just this gate delay, okay? So from this flop to this flop, total delay is, you have to consider this also, right? The clock to data delay also. It is actually 7 nanosecond plus 5 nanosecond. That is 12 nanosecond. Same way, can you tell me this clock to clock delay, clock to register delay? This is also 5 nanosecond. 5 nanosecond plus this delay, 8 nanosecond. It is 13 nanosecond. So these are actually which path? Register to register paths. Reg to reg path. Same way. So these are the input pins which may be coming from FPGA, right? These are the input pins. So we have another type of path, that is between your input pin to register path. Input pin to register path. So if you consider this input pin, Let me change the color of this input pin to register path. So if I say this is the input pin, so I have this path, right? One is this path, it is coming through this way, going through this way, this way, this way, and this is one path, right? And another path is this path. Do we have any other paths? Input pin to register paths, any other paths are there? Students, am I audible?
No, no, sir.
No. So what is the first path delay? If I consider this as A, this path as B, what is the path A's delay?
And
1 plus this 7, right? Input pin to reg path 1 nanosecond plus 7 nanosecond, path A, right? So another path B 1 nanosecond plus 8 nanosecond. So this is actually 8 nanosecond. Another is 9 nanosecond. This is another type of path, timing path what we have. So here also you are learning what are the different types of paths available, right? Paths available for timing analysis. So this is second type of path. Third type of path what we have, input pin to output pin path, direct path without any registers. Do we have such path, any such path? Without any sequential register, input to output, straight combinational path we have. Any such paths are there?
A2, why, sir?
Right. This path, right? This path.
Straight. Yes, yes.
Straight path. So what is the delay of that? 1 nanosecond plus
16, I
9
think.
nanosecond plus 6 nanosecond. So this is 16 nanosecond. This is another path. Fourth path, from flip-flop directly to output path. From flip-flop to output path. Any such paths are there? Flip-flop output to directly. Why? So this flip-flop anyway it is going, yeah. One is this path, right? This path. Can say K. And what is another path? This path, right? Yeah. What is the delay of K path? Flip-flop to out pin. This is another path. So what is the K path's delay? So this path delay is L path delay is 9 nanosecond plus 6 nanosecond, that is 15 nanosecond, right? No, 9,
6,
6 plus,
5.
correct, 5, that is 20 nanosecond. And another is 5 plus correct, U2, right? So 5 plus 9 plus 6. Both are same actually, right? Both are taking same paths.
Yes,
Both
sir.
are 20 nanosecond. So both are taking 9 plus 6 plus flip-flop delay 5. That is 20. Right? So while considering the F max, right? So you have to see. So here like maximum delay where we have 20 nanosecond, right? So with this actually we have to decide what is your maximum operating frequency. This way we have to analyze and decide our operational frequency of the circuit. And one more thing, it is also right important. If you see there are like some direct paths, right? Direct paths. So this will actually create lot of issues for timing analysis. I mean, like it's a straightforward path. Uh, like combinational circuit wise, like we don't know like what input frequency data we get and all, right? So always it is recommended for any circuit at the input and output we have to register. We have to put one register. So that like always register to register we can properly analyze what is the delay, right? Setup violation, hold violation, all this analysis we can do. Okay. And here whenever you analyze at this point, so if you see here this particular NAND gate, right? NAND gate. So in the interview, how they are asked, so how much time it takes if I give any input like A and clock, okay? So how much time it takes to stabilize the data at Y, Y. Okay, if I give any input, like if I at time 0.0 second, 0 nanosecond, that is a reference point. So they will ask you at reference 0 nanosecond, if I give some input, how much time it takes to stabilize the data. So such questions also they will ask. So it depends on clock also. And again, you have to see here, all the three inputs must get stabilized. Then only you will get, I mean, once all the three inputs of this NAND gate is stabilized, then after 9 nanosecond, you are going to get the proper output, right? That kind of analysis also you must do. Okay. So you can
Sir,
just
could you
take it
please
as a
repeat that point, sir?
yes. So in order to get the output stable here, why? After if I give input at this point 0 nanosecond, after how long I get Y stable Y? I mean I can consider Y. So it is not just like this path, right? Not only this path. So basically NAND of all the three paths, like it's a 3-input NAND gate and we have flip-flops, we have clock, all the three inputs I should get stable. Some at some time t, I will get stable, right? Because like if I see here, even though after 1 nanosecond, this A will be stable here. A will be stable here after 1 nanosecond. But corresponding to A, if I want other inputs to get stable, I have various data paths. Like here, if you consider this path, I have 8 nanosecond. See this 8 nanosecond, and this input will be this flip flop 5 nanosecond. After 5 nanosecond, this input will be stable. After that input is stable, plus 8 nanosecond, this input will be stable, and that is stable 5 plus 5 times this will be stable. So even though this is 1 nanosecond, so here it might be 8 plus 5, that is 13, plus we calculated various delays, right? So 12 nanosecond, So if you see here, like somewhere we have register path we calculated. So then we have to add this to your input to register path. Then we have to keep adding, and whichever we get maximum value at the input of this NAND gate, that will be one delay. We'll get some delay called K, delay K. Then delay K plus 9 nanosecond plus 20 nanosecond will be my final output delay, right? Hope you are getting what I'm trying to say.
So it is a sum of all delays. You mean to register,
Right,
register,
right, 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 right.
plus
In order to
clock,
get a
right, sir?
proper delay, right, we have to
Mm.
add like in those paths. Okay. So I'll give you some of the important formulas what you have to usually follow whenever you are analyzing any timing equations. The time period, the maximum frequency with which you operate the circuit, that is time period, is setup plus hold time, with which you can operate any flop actually. Clock period should be greater than that. Setup plus hold time. Okay. So the maximum delay of any flip flop, right? It should be less than clock period plus T capture, that is like where we are capturing the data, minus T launch minus T setup. Okay. The minimum delay for hold condition, the data time should be greater than the T capture minus T launch plus T hold. Okay. So these are some violation how we can resolve. I'll also offline I'll share you some of the circuitries, some codes. I was mentioning about uh, edge detection, pulse stretching. There are synchronization circuits and reset bridges. So those things I will share it in the group. Maybe like we will discuss sometime. Okay. So next class I will plan on HLS. That is the last class what I want to take. That is tomorrow I'll take. Okay. Any questions you have?
Yes, sir. So I have question regarding the resource utilization. Uh,
Hmm.
So actually, I have observed yesterday, like in my project, I have observed that I have some modules that's taking the resources like BRAMs.
Hmm.
Okay,
Hmm. Hmm.
so if when I added the BRAMs of all the modules, so it's giving 209. Like the total is 209, but when it's
Hmm.
reporting like the when the top function at the top function, the BRAM is 221.
Hmm. Hmm.
Like it
Why
means
it
the
is taking
actual.
more? You are asking, right? Why it is taking
Yes,
more?
like the actual and the reported are different.
Hmm. Hmm. See, there is actually there will be possibilities that some of your logics also might have inferred as block RAM. That is one possibility. Another possibility, even though you are computing that many block RAMs, okay,
Mm-hmm.
uh, how did you compute? Like you might have computed like how many bits required
No,
and
I added like suppose I have the top function, and inside
hmm,
top function I have some submodules. Okay,
hmm, hmm,
the first submodules is taking some I guess 25 BRAM, then the second
hmm,
one is taking 19, and third one is
hmm,
taking 33, fourth
hmm,
is 36, and the last one is 96. Okay, so when we'll add those um, VRAM's numbers. So it's giving 209. Okay.
hmm,
But the top function it's reporting us to 21.
While
So there are
integrating those
like,
submodule, yeah, while integrating those submodules, you might have used
Mhm.
some logics which might be inferring as block RAM basically. That is one possibility actually.
Then why it's
So
not
even
showing
logic,
in the report? I can't see those, like those 12, from where it's taking those 12s. I can't see those.
can you just, I mean, anyway, that report utilization summary, RPT report of the
Hmm.
implementation, if you can share me, right, I can analyze and let you know like where that is happening.
Yeah,
The
okay. So
report will be
for
generated,
tomorrow,
right?
I will prepare that Excel sheet, like so that I
Yes, yes.
can share you.
Instead of Excel, if you share me that report, RPT file of the implementation, that will have a detailed implementation and even the if there is any
So
trimming
for
or
that, maybe I can't share because it's like it would be
it
confidential.
doesn't contain any that doesn't contain any or RTL files, right? Implementation report will just contain the resource summaries. You can just if you see
No,
that
no,
like
that
any
I'm not saying because what I'm saying is it's not available on my computer, so which I can share. I can only share the Excel
okay
sheet
okay
that's on
okay okay
my
okay
computer. Yeah.
okay, okay. Sure, that you can.
Yes.
Okay, any other questions?
Yeah, that's also.
One more thing. You asked me to implement that power like DB
Right,
conversion, right, sir?
right, right.
Yeah. Yeah. Whether it is a power gear, you mean to implement
Yes, yes, I
voltage to
want
power conversion,
voltage to power conversion actually. Yeah, V square,
voltage
the
to power
20 log
conversion.
of V
Okay.
in
So
dB
they are
scale.
saying
So
like
that you have
there's
to
a no.
use usually you have to use some approximation methods. Like for
Yeah.
the
That
log computation is not possible in like digital straightforward, right? So you may have to use some
the
lookup table and approximations.
natural logarithm like ln ln something.
Right, that is not
They're
possible
using that.
straightforward in very long.
Okay.
You have to use approximations.
So I have gone 2 to 3 courses on that.
Mhm.
Okay. But I don't think so. It will be work, sir.
Correct. It is like it's little tricky. I mean, you have to use some block RAM based mechanisms and all.
Docker based mechanism.
Yes,
Okay. Okay.
there will be some thesis. I'll search. I'll also search and share it to you some of the literature if possible.
Okay. Okay, sir. Fine.
Okay.
Okay, sir. Thank you.
Okay. Thank you. We'll meet tomorrow. Okay. Tomorrow timings I'll let you know. Thank you.
Okay, sir. Thank you. Bye.